For the periodic properties activity, we are working with 4 trends on the periodic table. We are working with the valence electron trend. That's a pretty easy one. As we go from left to right, it simply increases. Atomic diameter. As we go from left to right along a given period, it decreases. As we go down a group, it increases. Ionization energy, the first ionization energy, is the energy required to remove the highest energy valence electron from a neutral element in the gas phase. So it's given by that equation 1. The ionization energy increases from left to right on a given period, and it increases going up on the periodic table, up a given family. Electronegativity is a measure of the tendency of an atom in a molecule to attract shared electrons to itself. So within a molecule, we have electrons then in a covalent compound between the 2 nuclei, and of those 2 nuclei, the one that can pull the electrons, those shared electrons, to itself more has the greater electronegativity. Electronegativity increases on a period from left to right and increases upward on a given group. Fluorine has the largest electronegativity. We tend not to think of electronegativities for the noble gases because they really don't want any more electrons, but values are given on some tables or periodic tables for some of the larger noble gases. The charge, so Z effective, we talked about in a lot of detail in the Chapter 7 handout, so review that. For this lab exercise, it's helpful to do a quick review. So if we're comparing the Z effective, the outermost electron in lithium fields versus that in nitrogen and fluorine, what we would do is draw a simple diagram. So lithium has 3 protons in its nucleus and 3 electrons. 2 of them are in the n=1 shell, the last one in the n=2 shell. Well, those 2 n=1 electrons effectively reduce the charge by an amount of 2 that outermost electron feels. So the Z effective that outermost electron feels is roughly 3 minus 2 or 1. That means that plus 1 is what's pulling that electron into it. Now, if we do the same analysis for nitrogen with its 7 protons and 7 electrons, what we have are, of course, 2 in the n=1 shell, 5 in the n=2 shell, and the n=2, the n=1 electrons basically reduce the charge that those outer 5 each feel by about 2. So we have Z effective for the outermost electrons to be roughly 7 minus 2 or 5. Well, that means that those outermost electrons are feeling a much larger pull toward the nucleus in nitrogen than they are in lithium. That makes nitrogen a smaller atom than lithium, because in both lithium and nitrogen, the outermost electrons are in the n=2 shell. We can further support that argument with fluorine, which has 2 more electrons in the n=2 shell, but still those outer electrons they feel the pull in of 9 minus 2 or plus 7. So they feel an even greater pull inward, making fluorine smaller than nitrogen. So that's why the trend is for sizes to decrease as we go from left to right. It's the protons that are able to pull more strongly on those outermost electrons. And of course, the outermost electrons are the ones that determine the size of the atom. Now, if we compare lithium to sodium, sodium being below lithium on the periodic table, they both have the same number of valence electrons. Lithium, we drew the picture of above, so it's got that Z effective of about +1 for that outer electron. Notice the outer electron is in the n=2 shell. Sodium looks rather similar. Of course, we have a lot more protons and electrons, but the Z effective that outermost electron in the n=3 shell feels is about 11 minus all those core electrons, 10, equaling to also about +1. So in both lithium and sodium, the outermost electron is feeling roughly a +1 pull inward, but sodium's outermost electron is in the n=3 shell, so a larger shell than with lithium where it's in the n=2 shell. So that makes sodium larger than lithium. And that's why sizes increase going down a group. Alrighty, so we're answering lots of questions. As usual, you can skip the pre-activity and go straight into the report. If you feel you need to reread the Chapter 7 handout on periodic properties, it's toward the end of that handout. You will, at times, to answer questions in the report, you will need actual numerical values for atomic diameter or ionization energies. Those are not given in this activity. They are given in your Chapter 7 handout notes. So when you need actual values, go to your notes for those values. They are shown for diameter, atomic diameter, for the ionization energy, and for the electronegativity. Alrighty, so our first section is on the valence electrons, and you're stating the trend in questions 1 and 2. You're giving the number of valence electrons in 3. You're making a comparison in 4. In 5, you're giving the electron configuration. So that's using that noble gas electron configuration. So for nitrogen, the noble gas coming before it is helium. So you're going to start with helium in the square brackets and then give the last electrons. You show what atomic orbital they're in and how many there are. Let's see, like sulfur, the noble gas coming before it is neon, so you're going to start with neon. For iodine, it's krypton, so you're going to start with krypton, and then you continue on, rubidium, strontium, you go through the 4D atomic orbitals, and then you get to the 5s atomic or the 5p atomic orbitals, and you end there. So be sure to do those correctly. We have in G and H ions, so just remove electrons from the electron configuration for the original atom. Number 6, so we are told that chromium's expected electron configuration is argon, the noble gas coming before it, and then 4s2, 3d4. But it turns out in practice, from experiment, we see that the actual electron configuration is argon 4s1, 3d5. So one of those 4s electrons goes into the 3d atomic orbitals so that we have 5 unpaired 3D electrons and one unpaired 4s electron. And you're asked to give a possible explanation. Well, we did not talk about this in the handout. It is something that in Chem 2 it is discussed, so we will wait on question 6 until Chem 2. It turns out it's just lower energy. The 4s electrons are good shielders. They very much block the charge. So the Z effective that the 3D electrons feels when there's a lot of those S electrons is less. So it makes them at a higher energy. But if we take away one of those 4s electrons, then the charge that those 3D electrons feels is a little greater, making for a lower energy situation. So you need not answer question 6. Okay, then we have the atomic diameter trend and discontinuities, number 3. That's where you need to go to your chapter 7 handout and find atomic diameter values and see if there's any places where it doesn't follow the trend. For number 4, you can simply think of the trend to answer those questions, or you can look to the periodic table that is shown with the atomic diameter values. Okay, next we have ionization energy, so it has to do with the trend. And for the first couple problems, number 4, it is giving you the valence electron energy level diagram for nitrogen and oxygen, and we're given the ionization energies for nitrogen and oxygen. Now, according to the periodic table trend, the value for oxygen should be greater than the value for nitrogen, but it's actually lower. So look at the energy level diagram and try to think of a reason why it's a little bit easier to remove an oxygen outer electron than it is a nitrogen one. Number 5, you'll need to go to the chapter 7 handout and find actual values to be able to see if there's any discontinuities, any break in the trend. Okay, number 6 has you going back in the introduction to equation number 1, where it shows you that what the definition of the first ionization energy is. You're using lithium as the example, so you're including the phases and all that. Alrighty, then we have a comparison in number 7, electronegativity. So you're giving the trend for the first few problems, making comparison, and then you're just, for 4, 5, and 6, you're just using the trend to answer the questions about comparing electronegativity values. In 5 and 6, yes, you're applying that. We have this idea of ionic character. So the greater are the electronegativity the greater is the difference between the electronegativity values of two atoms that are bonded together, the more those electrons are pulled from the lower electronegativity atom to the higher electronegativity atom. The more ionic is the characteristic of that bond. So if we have two atoms A and B, they have if they have a large electronegativity difference between the two atoms, then they're going to have a pretty large ionic character. So think about electronegativity values from the trends to decide which of that group in number 5 has the highest ionic character and which of the groups in 6 has the lowest ionic character. Lowest ionic character would be when the atoms have the closest electronegativity values. And hydrogen, to think about where it fits into the trend for electronegativity, its value is about equal to that of carbon. All right, so then questions. The first couple of them have to do with atomic diameter. So go through the explanation that are in the intro for this lab write-up, having to do with the Z effective. And for 3 here with ionization energy, so basically once we know the atomic diameter trend, ionization energy follows in the sense that the smaller is the atom, the harder is it to remove its outermost electron. So ionization energy trend kind of follows the size trend, you might say, in like the opposite direction. For number 5, what I would suggest you do is make a graph, a rough graph of boiling point versus, let's see, how about versus atomic number? And then extend and put the data in for the different noble gases given, draw the best fit line through there, and then extend your line to this synthetic element OG based on its atomic number. And give an idea of what its predicted boiling point would be. Alrighty, so when you are done with all that work, then scan your report as a PDF file and submit it.